In this lecture, we'll talk some more about SOP, POS, and terminology, what it means to be a minimal circuit, and then finally we'll talk about card-not map and how we can come up with reduced SOP and POS expressions. First, a little terminology. So for SOP, variables can be a variety of symbols. Literals are simply variables and their complements. A product term is the and of literals. So for example, X, Y not Z, or A, Y, A not A, Z. An example of something that's not a product term is X and Y not, or A and X, or A not. A sum of products expression, or SOP expression, is the or the sum of one or more product terms. And then a min term is a product term in which each variable appears exactly once. So this is a special product term called a min term, and it is a product term. So min term is a product term in which each variable appears exactly once, either in complemented or uncomplemented form. So for example, for the function that has three variables x, y, z, min terms would look, for example, like this or this. Two examples here. If the function instead had four variables, x naught, y, z would not be a min term because it doesn't have the w variable. Now there are some standard forms in which we can express SOPs. These are called the canonical SOP form, or for short just min term form, or sometimes it's called the disjunctive normal form or the standard SOP form. We'll call this the canonical SOP form or min term form. So say for example I had a function a, b, and c that looked like this, the expression. Another way we can express this in canonical SOP form is to say this is the OR of min terms 3, corresponding when the input is 0, 1, 1, min term 5, 1, 0, 1, min term 6, and then min term 7. You could also write this as the OR of these four min terms. And also I could express this as the sum of min terms 3, 5, 6, and 7. All of these different ways of expressing the same function. Now if I wanted to put a SOP expression, say for example I had the expression y x naught wz or x wy. So I have an SOP expression, but I want to put this in canonical form. I could use Boolean algebra to do this. So for example, I could go ahead and add with my identity and complementarity properties the z naught to the second term. So this is a four variable function. Then I can distribute this out to get y x naught wz or x w naught yz or x w naught y z naught, which is the OR. So if I wanted to put these variables at a certain order, let's say this was equal to g w x y. This would be the OR of m11, min term 11, min term 7, and min term 6. Now with POS, the terminology is very similar. So I have sum terms rather than product terms though. And a sum term is the OR of literals. So for example, a sum term, valid sum terms could look something like this, or like this, or any sum of literals. Things that are not sum terms, obviously then, again, something like this is not, and something like this is not. So a product of sums, or a POS expression, is the AND of one or more sum terms. And for POS, we also have what are called max terms, which is the sum term in which each variable appears exactly once. So a max term, either in its complemented or uncomplemented form. And as you can probably guess, we also have the canonical POS form or the max term form. So again, say for example, I had the function A, B, and C. It looks like this, and the canonical POS form can also be written as the AND of max term 0. So when A, B, and C are all 0, this forces the output to be 0. If I have 0, 0, 1, max term 1, same thing, max term 2, and max term 4. You can also write this as the AND of these max terms, or the product of the max terms. If I wanted to put a POS expression in canonical PS form as an example of that, I would again can use Boolean algebra. So I have, say, this POS expression, but I'd like to put it in canonical POS. I'm going to use complementarity to add why not, and identity, the identity properties, both of those, to add this term in the middle here, why, and it was why not. And then I'll distribute that out to get x or y naught or z, first term, and then I'll distribute this out to get x naught or y or z naught, ended with x naught or y naught or z naught, which would be max term 2, max term 5, and max term 7. Okay, so now let's talk about if we wanted to convert between SOP and POS, how would we do that? And there's a couple different ways we can do this. Let me show you a couple different ways that you might want to do this. So going from SOP to POS, for example. So say, for example, I had an SOP expression, G, which is W, X naught, or Y, or B, Z. First approach I could take, I can just use algebra, specifically the distributive property. So W and X naught or Y or BZ equals, I can distribute out these first two, so I have W or Y ended with X naught or Y or BZ. And then I can distribute out this again to get W or Y ended with X naught. So I separated out the B and the Z, and then I can do this, and then I can distribute this one more time in each one of these groupings in the square brackets. So that's the first method, just using algebra and specifically the distributive property multiple times. Another approach is to complement twice and use De Morgan's. So the function G is the same thing as G complemented twice. Then I'll apply De Morgan's one more time. And then I'll distribute out everything underneath the complement. And then apply De Morgan's one more time. So I get the same result, just a slightly different approach. Another method to take would be taking the dual twice. A quick note on the dual. The dual of a Boolean expression is the same as expression, except we replace the 0 with a 1, all the 1s with 0s, and the ands we replace with an or, and the ors we replace with an and. So for example, the dual of the expression x or y and 0 is x and y or 1. An important thing to note here is that the dual of an expression is not equivalent. And by the way, another important observation here is that the complement, obviously, and this is one of our Boolean properties, is also not equivalent. However, there is something called the principle of duality that is very useful, which says that if we know that two expressions are equal, say expressions E1 and E2, then we also know that the dual of the expression 1 is equivalent to the dual of expression E2. So even though the dual of the expression does not equal the original expression, if we have an equation, we know the duals of either side of the equation are also equivalent. So this can be handy when trying to prove equivalency in different types of Boolean proofs. Notice that you've already also seen the dual before. When we were looking at Boolean properties, there was two columns, and for one row, one property, say for example the identity, we're showing both versions of that property, and it's simply the dual of it using ors and ands or ones and zeros on either side. Okay, so coming back to converting between SOP and POS, if I take the dual twice, I can also do this conversion from SOP to POS. So for example, so I take the dual once, and I get something like this, W or X naught and Y, and with V or Z. Then I'm going to distribute out all of this again, and then I'll take the dual one more time. And so I get the same thing. So you can use any of these methods, but actually the method that I would recommend, that I would use, is just to distribute everything out. So I'm going to call this method 0 because I think it's the best. And the idea is just to multiply everything out. So my original expression is W, X naught, or Y, or VZ. And I'm going to pick one variable from each grouping and just go ahead and multiply this out. So I get W, or Y, or V, W, or Y, or Z, X naught, or Y, or V, X naught, or Y, or Z. One step, and I go straight to the result.